Hello. Also, friendly reminder, gummy worms are the greatest thing that has ever happened to me in quarantine. But let's not talk about that right now. Instead, let's have a cliche mathematics YouTube channel title card intro, whatever. Alright, welcome to my non-existent math YouTube channel, where today we will be talking about graphing integrals and derivatives. We won't be doing that too much mathematics stuff, because who cares? Let me hear it, who cares? Ooh, looks like we got the results in. Let's take a look at this. Oh yeah, literally no one. Look, there's even a smiley face there. People are happy about it. Just kidding. We will be doing a little bit of math, but not too much, so you don't have to think. At least not as much as I have to. So let's put on some bumpin' tunes right now and get into it. Ooh, peaceful. Alright, let's define our terms that we need to be concerned with today. So we'll be working with mainly derivative, which is not to be confused with something that is imitative of the work of another person. Instead, we're going to go into more definitions and word origin down here and find out that the mathematics definition is that it is an expression representing the rate of change of a function with respect to an independent variable, which you should know is also just slope. Okay, cool, sick. And the other term we're working with is integral. Not as much, but it's involved. Not to be concerned with integral, which is necessary to make a whole complete, that it's essential or fundamental. Instead, we're talking about this definition down here. A function of which a given function is the derivative. So basically doing the reverse of a derivative. It's kind of like wiping the makeup off of a function to find the original function. Alright, cool. So let's take a quick little peek at an example. Let's start with 2x cubed plus x squared plus 2. And we have it all in here in Desmos. We have the first derivative, second derivative, the antiderivative of the first derivative, all in here. I just want to take a quick little peek at some of the stuff we're going to be looking at. So here's our original function. Kind of looks like a side of a mountain. You know, it's kind of going up, but you're not quite at that peak on the other side. But we notice that there's a point of inflection here. First derivative, we have that U upwards concavity shape thing, and we notice that there's a local minimum at the bottom here, and it's in line with that point of inflection from the original function. Now let's put the little laser pointer in of a second derivative. It kind of just shoots through all this. It's kind of hard to determine what it's doing, but it is pretty much a straight line. And we notice that the 0 here is kind of in line with that local minimum and the point of inflection up here. So yes, let's talk about that. In a derivative, when you're graphing it, one of the first things you're going to look for is the point of inflection of the original function. When looking at an original function, you want to take note of all of those POIs, which I like to call them, and you'll recognize that each of those will represent a local minimum or maximum. And we'll talk about that soon, but just recognize that you notice that they're directly in line with each other. Now let's get rid of that original function and let's look at the second derivative. Now a big rule, main focus for finding second derivatives is instead of looking at those points of inflection first, you may want to look at the local sums and, local minimums and local maximums. And you want to take note of each and every single one of those, because you'll see that each of those mark the zeros, and you don't really have to do the math for those ones. You can kind of just go down and be like, alright, it's right there. So yeah, there you go, and it's right in line with that. And now let's talk about the antiderivatives, right? Antiderivatives, especially with graphing, when you're trying to graph the original function, or let's say you have the second derivative, you want to find the first derivative, It can be a little bit difficult, but just realize that you need to look at these rules and these aspects kind of in reverse. So you would instead, well, I mean, you get the plus c from the antiderivative, so it can kind of end up anywhere. I wanted to leave this part in here specifically so you can recognize that the POI and the local sum, they don't really leave each other, right? They're always kind of in line, which is a great note to have. But let's stop wasting time here and move on to the actual example, right? We'll keep that. Look at my background, right? Beautiful. Now let's move on to the most technologically advanced application on my computer, MS Paint. That's right, Mac users. This is limited edition stuff right here. Okay, so let's kind of draw a sloppy, I don't really like that. Let's make it a little bigger. Yeah, all right. Sick. Okay, so the example I want to do today for us is this one. I'm going to be drawing all this, so please don't make fun of me if it looks quite awful, but we're going to have x to the 4th minus 2x squared as our original function. We want to take the first derivative of that, and we'll use power rule, and we'll use that to recognize that will bring down the 4, right? And we only subtract 1, so it's going to be cubed up here, minus, bring down this 2 over here, and we'll go 2 times 2, we'll get 4x. That is our first derivative. Awesome. And because I don't want to waste too much time, let's just do the second derivative. We know how it goes. 3 times 4. Going to get 12x squared. And we're going to get rid of this x over here and make it into a little star for the top of your Christmas tree. We're going to get 4. Okay, now that we have our main focuses, we're going to kind of draw them out. So x to the 4th minus 2x squared. Please don't blame me if it's a little bit off, but I know that there is most definitely a 0 at 0 here. So it's going to come down from the left, right? It's going to kind of bounce up. It's going to hit this 0. It's going to come back down, and it's going to go back up. All right, that looks kind of gross, but it is a W if I've ever seen one, which is going to be very helpful for us. So let's graph this first derivative in red. Now we're going to be looking here for these points of inflection. We've got one here and one here, and we've got zeros right at these local minimums here that just go straight there. Now let's talk about maximums and minimums like I said I would earlier. So what you're going to want to look for, mathematically at least, is you're going to want to take the derivative of a function, right here, and you're going to want to set that equal to 0 to mathematically find the local minimums, maximum values there, and you're going to test the zeros in the first derivative, and you're going to find where it's positive, where it's negative. And if it's positive before and negative afterwards, that is going to be a local maximum. Now, if it's negative before and positive afterwards, that is going to be a local minimum. So let's look here at the points of inflection. So here's how you do it graphically. You're going to see that it kind of starts positive and then goes negative here. So we're going to have, here, let me get my red pen out. So we're going to have this local maximum right here. We have this 0 here, so we're going to take note of that. And then we're going to come around. Now we must acknowledge that because it touches 0 here, that there's also going to be a 0 for the first derivative right here. So we're going to come down. And now we notice that we're going from negative to positive. So we're going to have a local minimum. Yay! We're going to come down here, and then we're going to realize that we have to go back up close to where that 0 is. My drawing talent is straight garbage, but we're not going to worry about that. And now we're going to talk about this second derivative here. We have a point of inflection kind of right around here, right? And we're going to have zeros right here. I think you guys are getting the general theme of things. And now we're going to acknowledge that we're going from negative to positive. So we're going to have this beautiful upwards U function right here. And there you have it. There you have it, ladies and gentlemen. We kind of more or less predicted the graph's outline without any actual mathematics. Now let's look at how it's actually supposed to look. Now, this is not half bad, right? We have that original function that kind of comes in here looking like that W, and then we have that little S-twisty curve coming on through here, and then we have that big final second derivative U. And I'd say that's pretty darn good. Now, while I am out of time here, I would like to address some more mathematic ways to help you graph this stuff. When you do find, did not want that in blue. When you do find your zeros here with the derivative, you're going to take those and you're most likely going to plug them in right here. I'm not going to do it exactly for this, but let's just say you have -1, 0, 1. You're going to plug in numbers between 0 and -1, and you're going to be like, okay, it's negative there, and you're going to plug in numbers from 0 to 1. You're going to be like, okay, it's positive there, right? And because of how you find minimums and maximums, you'd acknowledge that this is going to be a local minimum. Yay! And it's going to look like that. And same kind of difference, right? We get 0, 1. Oh, that kind of looks like an 8. I'm sorry, but deal with it. You got a positive and a negative, and you're going to acknowledge that that is a local maximum. And in order to find absolute maximums and minimums, obviously you're going to take those points in, and you're going to look for the biggest y value point for each of the zeros, and you're going to be pretty much good with that. So I think that pretty much settles it. I think you could probably be able to predict any derivative, antiderivative graph just with these small things. So thank you for watching. Have a great day.